Okay, so welcome back. So in this video, we will be talking about elastic collision. Elastic collision is basically a collision where they don't touch each other. So it's a perfect collision. So an example of elastic collision are carts. For example, inside the lab where we have two carts that are about to hit each other. Let's say this is cart number 1, where you have the wheels. And at the end of the cart, you have a spring. And then there's another cart that is about to hit the first cart. So this is what we call elastic collision. It's a collision where two objects don't hit each other, or two bodies don't technically hit each other, but there is a collision. It's a perfect collision. Another cause of this perfect collision, maybe another cart. Okay, so we have two carts, and then we have another one on the left where both of them will collide. Just forgot to draw the arrows earlier, so both of them are moving towards each other. And same thing with this next pair of carts, but this time we have magnets. Okay, so we have magnets, and if we have, let's say both of them would have north and north, magnet will repel. Okay, so magnet will repel. So we all know immediately, as soon as they reach very close to each other, it will be pushed away from each other. So basically, the existence of a spring and a magnet would have what we call elastic collision. So it's a perfect collision. It's a perfect collision, but they don't touch each other. Okay, they don't touch each other. Let me just write down and label it using a different color. So here's the presence of a spring. I'll just lower it down so you can see. So a spring, and on this side we have magnets. So magnets, run out of ink. Dried up. Okay, so it dried up. Where's the other pen that I have here that is red, or close to be red? So we have magnets. Okay, so we have magnets of same pole. Why did I say it's a perfect collision? Perfect collision because the first condition in order to be considered as perfect collision is that the total momentum, okay, so the total momentum before collision is equal to the total momentum after collision. So collision momentum is conserved. Okay, so momentum is conserved, so it means that there's no external force causing it to slow down or change direction or reduce the speed of the objects after collision. So they're about to hit each other and then bounce off, hit each other and then bounce off. Second information that we should know about elastic collision is that the total kinetic energy before collision is equivalent or the same as the total kinetic energy after the collision. Okay, so two conditions: total momentum is conserved and total kinetic energy is conserved. Again, total kinetic energy and not the individual kinetic energy of the components. Let me just write here, momentum is mass multiplied by the velocity, and kinetic energy is 1/2 mv squared. So best way for us to understand this is to go over an example. And in this example, we have a 4-kilogram ball moving at 8 meters per second to the right, which collides with a 1-kilogram ball at rest. Okay, at rest. So there's two balls. One of them is 4 kilograms in terms of mass and it's moving to the right at 8 meters per second. So let's draw a diagram. So first thing that we should do is draw a diagram. Okay. So first object would possess a mass of 4 kilograms, and it's moving to the right at an initial velocity v sub I uppercase because it's the first object, and that is 8 meters per second. It's positive because it's moving to the right. Now the second object, which is 1 kilogram, is not moving because it says over here at rest. So at rest, it means it's not moving, so the initial velocity of the object will be equivalent to 0. And if there's no velocity, there is no momentum because it's not moving. There's also 0 kinetic energy. Okay. Now, next is to draw the diagram after collision. According to the problem, still, the mass didn't change. Again, just like what I mentioned in the previous videos we have, mass will not be affected in this collision as we are not going to damage or destroy the matter or destroy the object that will be involved in collision. It is still moving to the right, but at this time, the final velocity, which is represented by uppercase V with a subscript of F, is 4.8 meters per second. So it means there was a reduction or slows down. Yes, it will slow down because you hit another object that is not moving. So therefore, it will slow down in order to fulfill what we call the law of physics. Okay, if you hit or another object collides with another object, especially if it's not moving, what will happen is the object that is with more momentum will definitely transfer some of the momentum to the other object with lesser momentum. Just like in the law of conservation of energy. Law of conservation of energy, the total energy will be the same. But since a portion of the potential energy, let's say potential energy a certain height, as an object rolls down a ramp, what happens is that the potential energy is reduced, and that reduction is being transferred to the speed, which is the kinetic energy. In this case, it's the same thing. So now, for our object, the second object, which is 1 kilogram, question is, let us solve for the velocity. What is the velocity of the 1 kilogram object ball? So what is the velocity? So velocity entails not only the magnitude or the amount, how fast is it moving? So V sub F. So we're going to solve for it. But right now, we can basically come up with an assumption that the object is moving to the right after collision. Without even using your calculations, okay, without even calculating, you know right away that it will move to the right because this object, after it collided with the second object, or the bigger object, the 4 kilogram object collided with the 1 kilogram object that is not moving, continues to move at 4.8 meters per second to the right. So it means that this object should also be moving to the right because it can never move to the opposite direction without colliding again with the object, and does not follow the rule of physics. So therefore, it will move to the right. And of course, if it is slower than this velocity of the 4 kilogram, they will collide again. So definitely this speed should be greater than 4.8. So before you solve anything, you should anticipate what would happen. So by anticipating what do you think will happen, it will guide you in terms of getting the correct answer. So what I'm going to do is solve this by analyzing the initial condition. Right here where we have the momentum of the first object, I just do a shortcut where the momentum of the first object before, okay, you know what, before, so that's m v sub I, momentum before for the second object is mv sub I, lowercase. The first one is uppercase. So our mass is 4 multiplied by velocity of 8. Mass of 1 multiplied by velocity of 0 because it's not moving. So any number multiplied by 0 is 0. 4 times 8 is equivalent to 32. So this is 32 kilogram meters per second. Again, just like what we did in the previous question, let's add the momentum before the collision. So we would have the total momentum before collision is simply 32 kilogram meters per second. So that is the first one. So the first section. First section that we have. Elastic collision. First condition. So in the second condition, let's figure out the velocity after the collision, or the momentum after collision. So it's the same procedure. Uppercase multiplied by uppercase mass, uppercase velocity, but this time it's your final velocity, which will give us 4 times 4.8. And then you have mass and velocity, lowercase, which represent the second object, is 1 kilogram multiplied by v sub f. Multiplying 4 and 4.8, that will give us 19.2 kilogram meters per second. And this one will give us v sub f. 1 times v sub f, so we can just ignore 1. Therefore, if we add this, so the total momentum before is equivalent to 19.2 plus v sub f. So that will be our answer. Okay. However, this is not what we're trying to solve for. Okay, we're not trying to solve for the total momentum before and after, but instead we want to figure out the final velocity. But since we know that this total momentum before collision is the same as the total momentum after, and I said before, let me just correct myself, this is after. So now let's equate these two information that they should be equal to each other. So these two information should be equal. So now I can say that 32 is equal to 19.2 plus v sub f. Okay, 19.2 plus v sub f. Now, 19.2 times v sub f. Let's simplify this mathematically. All we have to do is subtract 19.2 on both sides. So I will subtract 19.2, and over here is negative 19.2, or subtract 19.2, so this will give us 0 plus v sub f, and that is equivalent to 32, which is 12.8. Now we can further explain or write that the velocity, or the final velocity, is 12.8 meters per second, and it's positive, so it means that our assumption that it's going to the right is correct, plus the assumption that it's going faster than v sub f of the mass, or the final velocity of the 4 kilogram mass, is correct because it's 12.8. So it means it will not hit each other anymore after the collision. Now, what if I want to add a second part for this question? So what I'm going to do is to move this a little bit higher, and let's add an extra question. Let's add an extra question, as I always like to do. Is the collision, so let's ask this question, is the collision elastic, or inelastic. So for us to answer this question, we need to figure out, not to figure out, but we need to satisfy the condition that the momentum is conserved. Okay? That the momentum is conserved. At second, we need to know if the velocity, the kinetic energy is also conserved. So why don't we try to figure out, okay, if both of those conditions are conserved? Now, all we have to do right now is total before is 32 kilogram, okay? So let's write it down from our calculation, okay, from the previous calculation. Let me just use a different color ink so you can see. So previous calculation, the total momentum before is 32 kilogram meter per second. And for the second one, which is for our momentum, okay, so what is the total? So we have 19.2 after collision kilogram meters per second. Now for the second one, now that we know the value of velocity, so we can just plug it in. So that is 1 multiplied by 12.8 kilogram meters per second. So when you add 19.2 plus 12.8, definitely that's 0. Carry 1, so that is 2. That means that is 32. So the total momentum after collision is also 32 kilograms per meter per second. 32 kilogram per meters per second. So it means that in terms of our momentum, yes. So we were able to satisfy the condition. Okay. However, okay, just like in the previous video, we have discussed, or it was mentioned there, that all collision, provided that there's no external force affecting, okay, there's no external force affecting the system, then the momentum will be conserved. Right here, it's already conserved. This one is conserved. So it's 32 kilogram meters per second on both cases. So in terms of momentum, we're safe. We're good. Now let's figure out what happened in terms of the kinetic energy. So for the entire system. So kinetic energy. So total kinetic energy. So let's write down the equation. Total kinetic energy before the collision. Let's plug it in. If kinetic energy is 1/2 mv squared, which is mass, the initial velocity, uppercase squared. So that means that's 1/2 multiplied by 4 times 8 squared. The second one, which is the 2 kilogram object, or 1 kilogram object, is lowercase m, lowercase v sub I squared, which is 1/2 1 multiplied by 0 squared. Multiplied by 0 squared. So that will be our next point. Okay, next point. This one, definitely it will be 0. On the other one, 8 times 8 times 4 divided by 2. So just trust me in terms of my calculation. I've done the calculation earlier. So all we have to do is just multiply and divide, or take the square of 8 multiplied by 4 divided by 2. Order of operation. So the total kinetic energy before collision is the sum of 128 and 0. So this will give us 128 joules. Now let's proceed with a calculation for the total kinetic energy after collision. So after they collided, 1 half m v sub f squared, which is equivalent to 1 half 4 multiplied by the square of 4.8. The second number is 1 half m v sub f squared, which is 1 half 1 multiplied by 12.8, which we have calculated earlier. It's right here, 12.8. So this will provide us an answer of 46.08 joules and 81.92 joules. So if you add those two numbers to determine the total kinetic after the collision, this will give us a total of 128 joules. With this, since the momentum and kinetic energies are the same before and after collision, so therefore the collision is elastic. So it's not inelastic but elastic. Okay. It's elastic. Oops, it's not a question, it's a statement. So that's our period. And let me just correct the total momentum and total kinetic energy. So both of them should be the total, not the individual energies, not the individual momentum of each object. And this proves that this collision is basically elastic and not inelastic. In the next video, we will discuss and just confirm the difference between elastic and inelastic collision, and also work on an example for us to act as guide as we learn the science of collision.